Okay, so I'm going to go over the two problems that I assigned as special problems from the previous session. So that was 5.4, limit comparison test. I'm going to only do the limit comparison test, and you're going to get soon, I'll announce it whenever, a quiz on this topic, and it will be something like the problems that I assigned. So let's do the first one. This one is from the book 206, number 206 from 5.4. And we have, this is the series, fourth root of n divided by the cube root of n to the fourth plus n squared. Okay, so why is the limit comparison test? Because we are talking here about something that, well, they're radicals, but they're also polynomials. So it's a mixture of radicals and polynomials. This type of functions, they remind us of the p-series. Okay, and then the next example that we'll do is something that reminds us of the geometric series. So therefore, what we're going to do is, in this kind of situation, we're going to choose a bn. That is the new, so these are the ans, right? In our general theory, this is always what we call an. So bn is going to be, how do we choose bn? Let me give myself a bit more space. The bn's, they are defined by, I'll do it in color, I take the highest degree term here, which, when I say highest degree term, I should look also at the fact that there are radicals involved. Perhaps the better way is to say the dominant term. Okay, so I'll say this is the dominant term here. There's of course only one, so it has to be that one. So I just take that. And I don't even convert the radical, notice that. It is something for later. And then what's now in the denominator? Well, it's the highest degree, but there is still the radical, so it is the cube root of n to the fourth. Okay, so that's my bn gonna be. And what is it that I need to do with this bn? And this is important, you have to, so this is, if you want, step 1. So what is step 2? Is now you have to show that this bn does what it needs to be doing, is namely this limit should not be 0 or should not be infinity. So let's calculate this limit. And the way we do this is, don't forget it's a limit still, we divide tops by tops and bottoms by bottoms. Again, if you don't think this is correct, try it out and with some examples and see with the simple fractions, and you'll see this is exactly correct what we do. We have the division of an by bn can be carried out by dividing the numerator of an divided by, I do it in the different color that you see it, the numerator of bn. So here comes the numerator of bn. And now we do the same for the denominators. We take the denominator, the entire denominator, be careful of course. So third n to the fourth plus n squared. For an, and then we do the same for bn, that will become our denominator here. Okay, that's how we do it. Why do we do this? Because now we can easily carry out the divisions after we bring everything inside the radicals. The top, we have a fourth radical and a fourth radical. Of course they cancel each other out, but I'm just saying it in general. In general, there might be more terms here, right? So we now rewrite this radical as the radical of the fraction. That's a valid operation with radicals and fractions. And do the same in the bottom. So it's the total radical of the fraction n for the fourth over n squared divided by n to the fourth. Okay? Because now we can do the division. Of course, these two just cancel out. But be careful here. This is a division in the bottom here. We have to divide a sum. That means we have to divide each of the terms. So the result will be on top. Let me just go here. On top, of course, we said that was just 1. It's the fourth root of 1. Okay, let me write it, but that is 1, right? I'm just writing it so that you see where it comes from. In the bottom, we have the third root of, well, we divide this and we divide there. We have to do both. 1 plus n squared divided by n fourth is 1 over n squared. And then, now if I plug in infinity, right, this limit is always trying to plug in infinity, I get 1 over infinity squared, that is 0, so this is 0. And what is left is the fourth root of 1 divided by the third root of 1, which is all 1. Now, is it a matter, should it be less than 1, bigger one? No. What matters here is, I'll do this in a color, in different color, is that, I'll do a different one, that this is not 0 or infinity. Now, this is not the end of the story, okay? This just means, good, you can go on. You can go, so this tells me, now go to step 3. And that's the step where we really carry out the convergence divergence test. Namely, what do we do in step 3? We go back to this Bn. So let me copy the Bn that I had here, this one. Fourth root of n on top and the cube root of n to the fourth in the bottom. And now I want to write this as a single power of n. And remember, in the P series, the power is in the bottom. Well, first of all, I'm converting the powers into rational exponents, 1/4, because it's the fourth root, divided by, and here, 4/3. It's the third root of a fourth power, okay? And now bring all this in the denominator. That means you bring this guy down there, which means subtracting. So n 4/3 minus 1/4. Now what matters is now, so P is 4/3 minus 1/4, right? Remember, in the P series, it always looks like 1 over n to the P. So this is what we see here, and this is therefore P is this number. And now the question is this bigger than 1 or not? Okay, let's work that out, what that is. I have to put this on common denominator 12, so 16. Right, so just quickly, times 4 times 4, 16/12. And here do times 3 minus 3/12. So I get 13/12, and that's just bigger than 1. Now what is this? In the P series, if P is bigger than 1, we get convergence. So that's the case we are in here. If P less than 1, we would, or equal to 1, we would have divergence, right? Okay. So this is a convergence series. Okay. So this is a series that look like a P series, and this is basically rational functions and radicals. Okay. So now the example that I gave you, there are no good examples in the textbook, so I made some extra ones from the extra sheet, and that was number 3 from the homework problem sheet. I hope you found the sheet there. I'm gonna copy it. 3, 4 to the n plus 2 to the n divided by 3 to the n plus 5 times 2 to the n. Okay. What's the difference here? Is that the n's are in the exponent, so we are dealing with exponential functions, right? Here the n's were all powers of, they were all powers of n, rational powers, but they were powers of n. Here we have exponentials in n, and this therefore reminds of the geometric series. Why? Because I remind you, the geometric series looks like this, right? One way of writing the general formula is as A, that's the initial term, times r to the power n, where r is the ratio. Okay. So we do the same thing. We look for the dominant terms. Let's start looking for the dominant terms here. We have 3 things. There's a 3 here, but that's not really a power. That's just a coefficient. That's like having a 3 here, for instance. That's really, you have to treat this as a coefficient, right? Be careful. That's let me undo this, that you see here. There was a times here. We did 3 times 4 to the n. Okay? So 3 itself is not put to any power. And also, sometimes people think, oh, this is 12 to the n. No. 3 to the n times 4 to the n, yes, that is 12 to the n. If there's also an n there, if both are raised to the same power, then you can combine them. But this is not a power, this is just a coefficient. So be very careful. So this is not the case, right? I'll sketch it out and now I erase it so that nobody else sees these mistakes, right? Because that's not correct. Okay, good. So what we have, our dominant term, what is that? Yes, so the dominant term is going to be the power. We have a power 4n and 2n. Well, there are 2 powers, and clearly the higher the base, the more dominant it is. So the dominant term is 4 to the n, not with the 3. You could add the 3, but why? It makes things much harder. So, okay, I'm writing down Bn, and I decided the top is, the dominant term is 4 to the n. And in the bottom, we have 3 to the n plus 5 times to the n. Again, 5 is a coefficient, so it doesn't play, and the one we have is the 3 to the n. It's now the biggest, right? Because 2 to the n is a lower base, so 3 to the n. So this is really the choice that we make for Bn by choosing the dominant term. So this was step 1, okay, and then step 2 is same, although this is a different type of calculation, but we have to now calculate the limit for n going to infinity, an divided by Bn, okay, and we do the same thing, tops by tops, bottoms by bottoms, so we have 3 times 4 to the n plus 2 to the n divided by 4 to the n, and then here we have this guy, 3 to the n plus 5 times 2 to the n divided by this guy, 3 to the n, okay. We carry out this division to do the algebra. That's again, when we divide, be very careful, right? This is a sum that we are dealing with. So it's not just, you cannot just do this. That's not the answer. That's not how you simplify a fraction like this, because is a sum, so we have to divide every single term. So what we have is 3 times 4 to the n divided by 4 to the n, and so they cancel out. I'm going to already get rid of them, but the 3 doesn't cancel out. That's the only point I wanted to make here. So, but I'm going to get rid of them because it's only the 3 that left, sorry. But this is the first definition. Now, if I divide this, what do I get? Well, we get 2 to the n over 4 to the n. Okay, we can simplify this, and we will, but let me just continue with the bottom now. What do we do here? Same thing. We divide 3 to the n into here and into there. So we get a 1 from the first part, and the second term is 5 times 2 to the n over 3 to the n. Again, the 5 does not combine with the 2, right? That's the same. This is just a coefficient. There's no power on top of it. Okay. What is this now good for? Well, we have to write it slightly more different, because I'm now going to combine these powers as a single exponential, 2/4, which of course is a half. And then here also 1 plus 5 2/3 to the n. Now what is matters here is, I repeat, if the base is bigger than 1, then a to the n goes to infinity. If the base of a is less than 1, then a to the n goes to 0. This is exponential growth, and this is exponential decay. Okay, this is something that you studied before, I think, in pre-calculus and so on. Okay, so in the limit, I mean, right? So the picture, of course, yeah, I hope that you don't misinterpret the error here. The picture of this one would be something like that. The picture of this one would be something like that. Okay, well, something like that. Okay, so this is the case that we're interested in, this exponential decay, because in both cases we have, and that's because we chose the dominant terms, that we have to have, all these things have to now be smaller than 1, so that in the limit they all become 0. Okay, so that's the point here. So this actually will be 0, this actually will be 0, 5 times 0 is of course also 0. What are we left with? Well, we're left with 3 over 1, which is just 3. Now what matters is, again, that this is not 0 and not infinity. So we can go to step 3. If this would be 0 infinity, that means we made a wrong choice. This means this Bn that we've was chosen wrong. Of course, it also could mean we made a mistake. But okay, so step 3, we go now look at Bn. So now, right, let me call this, in case, inspect Bn. We're going to now take a closer look at Bn, but only now. That's the point. Don't do this already at this stage, but don't do too many. Wait for this step until now. So what is Bn? That was 4 to the n over 3 to the n, right? Yep. So again, I'm combining this as a single power exponential, and I look at the base. The base, so the base here is now bigger than 1. And bigger than 1 means exponential growth. So that, oh yeah, no, sorry, this is not what we, sorry. apologize. I got a little bit sidetracked here by my thing. What I'm saying is not wrong, and it actually means this, but what we actually really looking now is the geometric series, right? This is a geometric series, and what is R here? R is 4/3, which is bigger than 1, so we have divergence. Exactly for what I was explaining before, but this is what matters, right? We compare it with geometric series, and we get something bigger than 1. This means this series is divergent, so that means that the original series is divergent. Yeah, perhaps I forgot to say this. In the previous case, we found convergence, which of the B ends meant that actually this one was also convergent, right? Sorry, I forgot to draw the conclusion there. Okay, that's 2 homework problems, and so as I said, we'll go do a quiz soon. I'll perhaps put also a review, another one up there for a review, but I'll decide. I haven't decided yet exactly when we will do this.